Hi, welcome to another video. So this video is about this pressure sensor here. It's made by Honeywell and it's an absolute pressure sensor. So that means the output from this device, which is digital incidentally, I2C or SPI, the output will measure the current ambient pressure or atmospheric pressure. It's just over 1 bar. So I maybe picked the wrong one because this has got a 1.9mm tube. My pen tip, give you an idea how big it is. My fingers. So it's quite small. Yeah, here's some silicon tube, 1.8mm internal diameter. I've had to order from China because they're not available in Europe, or couldn't find any. Some adapters to step this up from 2 to 4 and 5mm. I wanted this because if you saw a recent video on a turbocharger problem I had, different gauges measure different pressures and there's no means to calibrate them. This being an electronic device, A, it's more accurate, and B, it can be calibrated. You can just alter the code. I got this from Mouser. I believe they're pronounced Mouser. There's an office here in the UK, but all the parts come from the US. So this has come from the US. So I'll put the wiring up later, but we've got power, ground, chip select, because I'm using SPI, 8-bit, and serial data out and serial clock. That's the 5 lines. Because this is running on a ribbon cable, which has got to be a good 8 inches long, ideally I should have a capacitor on the power pins, but it works really well without it. But first of all, when you're looking for the datasheet, you'll find this on many of the sites like RS, Mouser, Farnell. Scroll down to the bottom. And see there, sensing.honeywell.com. Go there, copy and paste it. Got the page open already. Support, technical support. Fill in this box because it's not really my place to dish out the PDF. Big shout out to Theodore. I've spoken to him on the phone once or twice. He responded to that request for a datasheet with it, before my coffee got cold. So Honeywell are very helpful to end users like you and I, and obviously big companies purchasing, I don't know, thousands, tens of thousands of units. So yeah, I've got to hand it to Honeywell. I'm impressed. So I think whilst scrolling through this datasheet, I think I found the address for the I2C communication. However, I wanted to implement SPI, so they sent me this datasheet. The important part is sampling the data. So here's the master in, slave out. So serial data into your microchip or Arduino, sampling the data on the rising edge of the clock. You see here that green line. The data is valid on the rising edge of the clock. If you get this wrong, your data will be wrong. And this status bit 0 will throw up a 1, meaning it thinks it's in command mode, which I believe is when the manufacturers are programming the EEPROM. I had this bit 1 here because I wasn't sampling the data in the right place. So sample the data at the rising edge of your SPI clock, assuming you're using SPI. There's a serial out from the pressure sensor, there's a chip select, there's the data from the pressure sensor. As I say, it's an absolute pressure sensor, so it measures vacuum as well. Status bit 1, status bit 0, we don't want these, we just want these last 14 bits. and you can read them individually, so byte 1, then byte 2, byte 3, byte 4. You don't have to have a 16 or 32-bit controller to read them. So we ignore the first 2 status bits, concentrate on the last 14 bits, and then the temperature, you have the option of reading 8-bit or 11-bit and excluding the last 5 bits. And I'll show you why it's important to exclude those last 5 bits. I'll show you on the screen. Very quickly, the datasheet explains how to calibrate your sensor, and it talks about 90% of the output and 10% of the output. And as I explained in my byte and picking bits tutorial, 2 to the power of 14, the count gives it 3999, and then hexadecimal 0666. So you should be familiar now. Put those numbers into the calculator, you see what bits you're picking out. But scrolling back up to the top of this page, it says that they've got some calculations and some examples from, I believe it was a -1 psi to 1 psi differential sensor. But all I did was grab 2 bits of data, exclude the first 2 bits, look at the data I had, look at the local pressure from the Met Office, divide one into the other, and I've had a very reliable pressure reading. One night before I went to bed, it was reading 1021 millibar. The next morning, it had gone up to over 1030 millibar. I thought, no, that can't be right. Check the pressure, and it was right. So I'll get this code out of the way first, then I don't have to come back to the PC. So I've got a buffer for the SPI, pressure count 1, which is the upper byte, pressure count 2, total count, and you can see there whether they're chars 8-bit or 16-bit integers, total count, pressure out, float out. I'll leave these examples in here. These are examples I was testing to make sure my floating point worked, and it corrects for the exponent, takes the exponent out and puts in the leading 0 point. I've left them in there. You can just uncomment them like that and try them if you like. But this video is not really about my floating point function, it's about the pressure sensor. But unless I show you part of the floating point function, you won't understand what it's doing. So if I go code, write float. Oh, incidentally, there's 2 fonts now. I had a larger one, which is too large for this screen, so I developed a smaller font. So you've now got the option of write float or write float large, which is larger font, and a write number somewhere, and a write number large. Here we are, write number, and then write number large. So because that doesn't say anything, you can assume it's the smaller font. I'll jump up to my float. Write float. So that we don't get any blank spaces when we're not using the characters, I've got these valid implemented now. That's all the positions for the numbers. At the moment, this is all commented out. And you can actually, a little tip, you can, for example, you can select all these commented functions, right click, and down to uncomment. So my main function that takes care of the exponent, cuts it out, puts a leading decimal place in, is one of these down here. If I explain 1, then you'll get the gist of the rest. Right, from the ASCII chart, the E is on the ASCII chart as a 101. And in fact, if you're using Microelectronica's IDE, go up to Tools, ASCII chart, 101, little e. So this function checks position 9 and 8 and 7, and it looks for the E. So in this case, it's position 9, looks for the E, and if the number after it, see this 45 back to the ASCII chart. That's actually, I know it's a dash or hyphen, so it looks for the E, then the hyphen, which is ASCII 45, then it looks for the dot, which is ASCII 46. Get rid of that. 45, I'm not looking for the dot here. Then it's looking for those strings of 9, so 57 is 9 on the ASCII chart. If it sees a string of 9s, and this one, if it sees a string of 9s, it looks for the E, and then what exponent, whether it's 1 or 2, in this case 49, I believe it's 1. ASCII chart, 49, yes, 1. So this would be exponent E negative 1. It makes all these functions invalid to cut out all the decimal places after, I think, 2. Copies the, so that would be the negative. That would be at like 9.8. So negative 9.8 copies them, puts a leading 0 in here, and then just puts the characters back in a different position. That's how my function corrects for errors, like rounds an 8 up to a 9, and gets rid of the exponent function or exponent value. So there's a function there for one class of numbers, another one here, another one here. If you're using numbers that are totally, I don't know, obscure and nothing like mine, maybe a number to like 6 decimal places, you can simply come here and add your own function. At least using this function, you are able to modify it. You're not able to modify it if you use Microelectronica's standard float. Right, so first of all, this is the first byte shifted left 8 places. This is the second byte raw data. This is a status bit. So remember, status bit 1 was to the value of 128, status bit 0 to the value of 64. If they were both on, we'd have 192. So something is going on here, and that's why I contacted Theodore. And he put me right. This PIC microcontroller was looking at the data at the wrong time, and it messes up the pressure and temperature. So we've got like 49.185 degrees to the negative 1. So what's that, 4.9 degrees? And our pressure, I believe, is measuring bar 0.343 bar. So that's totally wrong. So that's why it's important to look at those. There we are, that's sampling the data on the rising edge of the clock. Have a look at the code. If I've not said it before, I'll put it into Google Drive and put a link in the show more. If you've got any serious questions about the code and how it works, and I get enough of you saying, how does it work, can you please explain? I'll do another video on that, but for now this is just a pressure sensor and the basics. So this is using my floating point function, so no need to write it, blank it and write it again. Just put the data on the screen. Let me suck on this pipe. So this, that's currently showing 1.003 bar and 929. I didn't say earlier, but when that pressure changed from the evening to the morning, it was 0.001 of a bar accurate. Right, temperature, pressure. I've left the titles out for the minute so you can see what's happening. I'll suck on this pipe. There we go. So that's 5.54 to the minus 1. So you've got to move that decimal place. Left 1, and the same with his temperature. But why is his temperature changed when I sucked on this pipe? which I'm now holding. If I let go of this pipe, you can see the pressure shot back up, but I haven't cleared these yet. Let me suck on a pipe and watch the temperature again. This temperature is altering because I haven't excluded those last 5 bits, and so between the pressure and temperature, maybe just the temperature used as the last 5 bits, or there's some sharing going on. That's why Honeywell tell you to exclude the last 5 bits. So let me exclude the last 5 bits. Well, there we are. 24.23 degrees, 1.003 bar. Forget the 927, it's so small, not worth worrying about. Right, before I put these titles back in, let me suck on this pipe once more. So notice I still get the erroneous data here because I haven't excluded it from the display. But if you look at the main temperature, 24.26 degrees, forget the 208. Hopefully you'll see that 26 isn't changing. We're now down to 500 millibar, which is actually, after doing the turbo, they were saying to me, I'm talking of 5 pascals, it should have been 50 pascals. So they were wrong to say 5, it was 50, not 5. There we go, watch this 2.6. There's the pipe, let go. Right, so now using those valid functions, I've taken out everything from 5 upwards. So now we've got 1.003 bar and 24.38 degrees C. So let me suck on this pipe now and watch the pressure. There we go, the temperature didn't move, I don't think. And that's the pressure, 0.5 of a bar. There we go, 0.7. 0.5. So have a look at the floating point function in the C file. It's not an obfuscation competition, there is nothing hidden, it's all plain text, plain readable text. You can see exactly what the SPI is doing, which is how you communicate with these Honeywell sensors. But I can't leave you with just this. A code I had to search for, I put on YouTube a couple of years ago for a gauge. Let me program that. And that's the code I'm going to share with you. Well, I'll share this one as well if you like. So I'm currently using a PIC 32MZ microcontroller, but this will work with any 8-bit microcontroller or 16-bit, 32-bit. You might have to modify some of the code for different chips, but it's all free. None of it's hidden. One C file. Right, here's a quick look at the gauge. This was my larger font, and you can see I haven't removed all the data we don't need. This was my larger font, which is why I had to produce this smaller font. Let me get rid of this and use a small font. Right, this is the completed code. Everything in the floating point function uncommented, so it's all working. There's the temperature, which you can see is actually fluctuating by 1/10 of a degree. Far more stable than those other ones I demonstrated a few months ago with those thermocouples. So rock steady temperature, rock steady pressure. As I say, this gauge example isn't new. I put it on YouTube a couple of years ago. Couldn't find it on my PC, had to go looking for it. So if I suck on this pipe, there we are, that's the end of the pipe. And you can see my floating point function is putting a leading 0, getting rid of the exponent. There was no errors in this particular number. Let go of the pipe. It's very responsive. If I try and blow, it's actually easier to suck than blow. And that's as much as I can get into it. What I do have here is a blood pressure monitor. Right, what I'll do, I'll put this pipe, well, it's a bit small for this hole. It must have a small orifice inside because I can hold that there. If I get my hand out of the way. Hopefully this will work. Right, so my hands are sort of not in the way of the blue gauge. So that's 1.02 bar at the moment. If I turn this on, there we go. Can you see the 1.690 bar? And again, watch the blue gauge. There we go. So I know these go up to sort of 200-300 millimeters of mercury, which is actually sort of 0.2, 0.3 of a bar. But obviously that's on top of atmospheric pressure. So I'm obviously coming up to the limit of this pressure sensor. But I want it specifically for vacuum, not ambient pressure. So now that's settled at 102.1 bar. If I turn to a live view of the screen, hopefully that's in focus. So down here, 7 o'clock today, 1.020. So it's been, yeah, the pressure's been dropping. We actually had a bit of snow earlier. Hopefully that's in focus, I can't see. So 102. Yeah, it's fluctuating a bit, but I'm happy with the accuracy of that, considering I just took the raw data, divided it by the current pressure on that day, and I've got this value. So this is obviously bar, but being electronic, you can calibrate it in whatever scale you want. If I change this from a float to a whole number, and then change this to millibar, well, I've changed this to millibar, as you can see. This is now using my write number function. Just put in a number and it writes it. I've turned the light off because I just had to do this clip again. I was getting funny colour artifacts and distortion. Not sure if it's the light interfering with the scan rate of the camera and the screen, but it looked terrible, so that's why it's darker. So this millibar now, obviously no decimal point. If I could be bothered, you know, if it's less than 1,000, I could get it to move over by a few places. You can see it's warming up here. It's 24.0104 degrees, so very accurate temperature sensor. Oh, and I forgot to say, so obviously being a digital gauge, this is now millibar. It was bar, but you can convert it to inches of mercury, pascals, kilopascals, inches of water, whatever you want. The versatility of electronic pressure sensors. Yeah, so this is now one whole number and a floating point for the temperature. Hopefully it's given you some insight to Honeywell pressure sensors. I say pressure sensors because that's what they are, although this is measuring ambient pressure. And I can suck on the pipe, which is effectively, that's now measuring a partial vacuum, but still absolute pressure within this pipe. If you liked it, leave a comment, or got any questions, leave a comment. Thank you for watching.